episode 36, titled Time Series Basics, Trend, Seasonality, Noise, and Stationarity, the goal is to learn the main parts of time series so you choose models correctly. Because DataX questions often test whether you recognize that time-ordered data is a different kind of problem than a table of independent rows. When values are indexed by time, the order carries information, and many methods assume properties that are either stable over time or explicitly modeled as changing. If you ignore those properties, you can produce models that look great in evaluation and fail immediately in real use because time behavior violates the assumptions. This episode will define trend, seasonality, noise, and stationarity in plain language, then show how to spot non-stationary cues like drifting mean and changing variance. You will also learn why differencing and rolling averages are used, how autocorrelation reflects dependence, and why evaluation must respect time order. The exam rewards these concepts because they determine whether you split data correctly, choose appropriate features, and interpret performance honestly. By the end, you should be able to hear a time series scenario and quickly name what structure is present and what next step is safest. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Trend is the long-term direction of a series, separate from short swings, and it describes whether the level of the series is moving upward, downward, or staying flat over extended time. A trend is not the day-to-day wobble. It is the underlying drift you can see when you step back and look across a longer span. Trends can reflect growth, decline, adoption curves, or gradual degradation, and the exam often describes these in business terms like steady increase over months or gradual decline after a policy change. Recognizing trend matters because many models assume a stable mean, and a strong trend violates that assumption by shifting the level over time. It also matters because trend can be confused with one-time shifts, where the series jumps to a new level and stays there, which is not a repeating seasonal pattern. DataX rewards trend recognition because it helps you decide whether to model the level directly, transform the series, or use differencing to focus on change rather than absolute level. When you can separate long-term drift from short-term noise, you are reading the series correctly. Seasonality is a repeating pattern tied to calendar cycles, meaning the series tends to rise and fall in a consistent rhythm based on time of day of week, month of year, or other periodic schedules. Seasonality is not random. It repeats in a way that you can predict if you know the cycle, such as higher traffic on weekdays, higher sales during holidays, or higher load at certain hours. The exam often signals seasonality through language like recurs every week, spikes each quarter, or weekday versus weekend patterns. And those cues matter because they imply predictable structure. Seasonality differs from trend because it oscillates around a level, while trend moves the level itself. It also differs from noise because it is systematic, meaning it can be captured with features or models designed for periodic behavior. DataX rewards seasonality recognition because it affects both model choice and feature engineering, especially when you need to forecast or detect anomalies relative to expected seasonal baselines. When you can name the likely cycle, you are already ahead in time series interpretation. Noise is the randomness not explained by structure, and it is what remains after you account for trend, seasonality, and other systematic components. Noise can include measurement error, unpredictable shocks, and short-term fluctuations that do not repeat consistently. The presence of noise is normal. The key is to avoid treating noise as if it were structure, which leads to overfitting and false confidence. The exam may describe random fluctuations or unpredictable variability, and those phrases are hints that not every wiggle deserves a modeling explanation. Noise also matters because it determines how uncertain forecasts and anomaly thresholds should be. Higher noise implies wider uncertainty bounds. A common exam trap is choosing an overly complex model to chase noise, especially when a simpler decomposition or smoothing approach would capture the meaningful pattern. DataX rewards learners who can say what part of a series is structured and what part is noise, because that distinction is foundational for correct modeling and honest communication. When you treat noise as expected randomness, you choose more defensible methods. Stationarity is the idea that key statistical properties of the series stay stable over time, meaning the process does not change its behavior in ways that break the assumptions of many models. A stationary series has a stable mean and variance and consistent relationships over time, even though individual values still fluctuate. This does not mean the series is constant. It means its statistical behavior is stable enough that past patterns are informative about future patterns in a consistent way. Many classical time series methods assume stationarity or require a series to be transformed into a stationary form before modeling. The exam often tests stationarity because it determines whether differencing or other transformations are needed, and whether evaluation results can be generalized. Stationarity also connects to autocorrelation because stable dependence patterns are often part of what stationarity implies. DataX rewards stationarity understanding because it helps you decide whether you can treat the series as having stable structure or whether you must model change explicitly. When you can say that stationarity is stable statistical behavior over time, you are on the right track. Non-stationarity shows up when the mean drifts or variance changes, and the exam often describes these cues in plain language rather than in formal tests. A drifting mean can look like a trend, a level shift, or a gradual change in baseline, while changing variance can look like volatility increasing during peak periods or spreading out over time. The exam may describe a series becoming more volatile or having wider swings after a change, which indicates variance non-stationarity. Non-stationarity matters because it can cause models trained on earlier periods to fail later periods, and it can make confidence intervals and thresholds unreliable if you assume stability. It also matters because it can indicate drift, which requires monitoring and potentially retraining or recalibration. DataX rewards recognizing non-stationarity because it shows you are aware that time series are often influenced by evolving conditions, not static distributions. When you see shifting baselines and changing variability, you should become cautious about methods that assume a stable process. Differencing is a common response when trend dominates the signal, because differencing turns a level series into a change series by subtracting previous values from current values. Conceptually, differencing removes a persistent trend by focusing on increments, which can make the resulting series closer to stationary. The exam may describe a series with a strong upward drift and ask what transformation helps, and differencing is often the correct choice in that context. Differencing is not a cure for every time series problem, but it is a standard tool for removing trend-like behavior and stabilizing mean. It can also be applied seasonally, meaning you difference against a previous period in the cycle, when seasonal patterns dominate and you want to remove repeating structure. The key is to recognize that differencing changes what the series represents, shifting from level to change, which changes interpretation and evaluation. DataX rewards selecting differencing when trend is the main non-stationary feature because it reflects correct time series preprocessing intuition. Rolling averages are a conceptual smoothing tool that helps you reveal patterns by reducing short-term noise and highlighting trend and seasonality. A rolling average computes an average over a sliding window, which filters out high-frequency fluctuations and makes the underlying direction easier to see. The exam often mentions smoothing or rolling windows in time series contexts because they are intuitive and widely used for monitoring and visualization. Rolling averages can also serve as baselines for anomaly detection, where you compare current values to a smoothed expected level rather than to a single global mean. The key is that rolling averages introduce lag, meaning they respond slowly to sudden changes, which can be a feature or a limitation depending on the goal. In forecasting, rolling averages can help you understand the components before choosing a model. In monitoring, they can reduce false alarms caused by noise. DataX rewards this conceptual use because it shows you can apply smoothing to interpret time series behavior without overcomplicating the method. Autocorrelation captures dependence between past and future values, meaning current values are related to recent past values rather than being independent draws. In many time series, what happened recently influences what happens next, such as demand carrying momentum, systems having inertia, or error rates clustering in bursts. Autocorrelation is a way to describe that the series has memory, and the exam may hint at this through phrases like values tend to persist or spikes cluster, which implies dependence. Recognizing autocorrelation matters because many standard machine learning assumptions treat rows as independent, and autocorrelation violates that assumption. It also matters for model choice because time series models often include lagged values explicitly to capture this dependence. DataX rewards autocorrelation awareness because it supports correct split strategies and prevents leakage where the model accidentally learns from future adjacent information. When you recognize that time series has dependence, you treat ordering as meaningful rather than as a nuisance. A critical habit is to avoid treating time data like independent rows because order matters and random shuffling can contaminate evaluation and inflate performance. If you randomly shuffle time series rows into training and test sets, you create a situation where training data can include points that occur after test points, letting the model implicitly learn from the future. This produces evaluation results that look strong but do not reflect real forecasting or real-time prediction conditions. The exam often tests this by asking how to split time series data, and the correct answer is to use time-based splits that respect chronology. Order also matters for feature engineering because lag features must be computed using past values only, and leakage occurs if you compute them using information from the future. DataX rewards this because it is an integrity issue. Time series evaluation must reflect the real direction of time. When you treat time as a sequence, you choose methods and splits that are defensible. Evaluation splits for time series should be done by time, not by random shuffles, meaning you train on earlier periods and evaluate on later periods to mimic real deployment. This approach tests whether the model can generalize forward in time under drift and changing conditions, which is what matters in practice. The exam may describe backtesting, holdout windows, or training on historical data and forecasting future periods, and all of those imply time-based splitting. Time-based evaluation can also involve rolling windows, where you train on a moving history and test on the next segment repeatedly, providing a more robust view of performance across time. The key is that you never let the evaluation period influence training, directly or indirectly, because that breaks the realism of the test. DataX rewards choosing time-based splits because it demonstrates you understand time series as a forward-looking prediction problem rather than a static classification problem. When you split by time, your performance estimates become more trustworthy. Seasonality also connects to feature engineering through calendar indicators because many models need explicit features to capture repeating patterns. Calendar indicators include things like day of week, month, holiday flags, and hour of day, which provide structured signals about the cycle that the model can learn. The exam may describe recurring patterns and ask how to capture them, and the correct answer often involves adding calendar-based features or using models that can represent seasonal components. This is especially useful when you are not using a specialized time series model, because general machine learning models need explicit signals to represent periodic behavior. Calendar features can also help anomaly detection by letting you compare behavior to the appropriate seasonal baseline rather than to a global average. The key is to align the indicators with the true cycle in the domain, because incorrect cycles produce misleading patterns and poor generalization. DataX rewards this because it shows you can translate domain time structure into features that support predictive performance. A reliable anchor for time series thinking is that trend moves, season repeats, and stationarity stays stable because it keeps the components distinct under pressure. Trend is the long-run drift in level. Seasonality is the repeating cycle around a level. And stationarity is the stability of statistical behavior that many methods rely on. When you hear a scenario, you can ask which of these is present and which is being violated. And that guides your next step, such as differencing to remove trend or adding calendar features to capture seasonality. The anchor also helps you remember that non-stationarity is a warning sign because it implies that properties are changing and that models must be cautious. Under exam pressure, this anchor simplifies the problem into identifying components and then choosing a matching response. DataX rewards this because it produces consistent and correct decisions about preprocessing, modeling, and evaluation. When you can quickly name which component is dominant, you can answer method selection questions more reliably. To conclude episode 36, describe one time series and then name its key components, because that is the exam skill that turns a story into a modeling plan. Pick a series like weekly sales, hourly traffic, or daily fraud rate, and describe whether it has a long-term trend, a repeating seasonal cycle, and a level of noise that creates random fluctuations. Then state whether the series appears stationary or non-stationary, using cues like drifting mean or changing variance, and explain why that matters for model assumptions. If trend dominates, identify differencing as a way to stabilize the mean, and if seasonality is present, mention calendar indicators or seasonal adjustments as a way to capture repeating patterns. Finally, state that evaluation should respect time order and avoid random shuffling, because the sequence defines what information is legitimately available. If you can narrate that diagnosis clearly, you will handle DataX time series questions with calm, correct, and professionally defensible reasoning. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.